going to talk about extreme values of functions. Okay, we're going to describe local and global maxima and minima. We are going to find candidate extrema, and then we are going to find global extrema. That's what we're going to talk about. Okay, one of the most important applications of calculus, particularly differential calculus, is optimization. Okay, so finding, for instance, the values of inputs that maximize or minimize a certain output. Okay, you want to make something as big as possible or as small as possible. For example, you don't have to write this down. Okay, examples. Okay, suppose you want to adjust the growing conditions for a crop or bacteria or something else, okay, to maximize their growth rate. That's something that's commonly done, and that's a case of optimization. If you want to determine what dose of a drug you should apply to an individual to make them as well as possible, that's optimization. Incidentally, optimization is a huge field, okay? It's not just what we're going to talk about today. Okay, when you want to make a journey in the shortest possible time, you're minimizing time, that's optimization. This shows up a lot in business or manufacturing. You want to minimize the cost associated with producing something, or maximize your profit. And here's something you'll see if you like animals, optimal foraging theory. When animals need to decide how much to eat, what to eat, how long to stay a certain place eating stuff, depending on such things as how often they encounter various types of prey, the energy content of the prey, how long it takes to handle the prey, how long it takes them to deplete a patch they're in, that kind of thing. It turns out that they essentially optimize what they get from their environment, okay? So optimal foraging theory describes the behavior of animals in terms of optimizing, let's say, how much energy they pick up from their eating. And there's a lot of mathematical modeling in that area. Okay, oodles of applications of optimization, and it's a big deal in differential calculus. Okay, so we're trying to find out when something is made as big as possible or as small as possible, so what we wind up looking for, we're looking for maximum or minimum and minimum values of functions. Okay, and maximum and minimum values are called extreme values or extrema. Okay, so I might say extrema, optima, I'm saying maxima or minima. Okay. Okay, next class we're going to be talking about the shapes of graphs, and we're going to see a lot of extrema there. And on Monday we're going to talk about optimization, so we'll be doing more sort of applied examples of this kind of stuff. So the next 3 lectures will be related, including this one. Okay? Awesome, let's draw a picture. Consider this function. Okay, A, B. Okay, consider me. Okay, so we're going to talk about extreme values. Here's your definition. Global or absolute extreme values. We consider a function f on an interval I in its domain. I panicked a lot yesterday about how to write these things. So it probably doesn't have to be an interval I. If you just say over a domain, that's good enough. Okay, this is probably too strict a definition of this. Consider a function f on an interval I in its domain or a domain if there is a number c in that interval or in the domain such that the function's value at c beats or ties the function's value everywhere in I, then f at c is the global or absolute maximum value of f on I. That's the kind of definition you need if you're trying to prove stuff, okay? If you're trying to really understand things. Okay, go through that a couple times and tie it to an intuitive understanding of what we're talking about. Okay, and similarly for minimum. Okay, so what are we talking about? We're saying that if the function achieves a value that's the highest point in the function, essentially, you call that a global or absolute maximum. The lowest point is associated with the global or absolute minimum. That's all that says. Okay? Try to be mathematically literate and understand that that means what I just said. Okay. Global and absolute mean the same thing. If someone doesn't tell you the interval, then you just assume it's the whole domain. Sometimes we don't say global or absolute at all. We just say look for the minimum or the maximum. We mean the global one. By we, I don't just mean in this course. I mean generally. When someone says maximize something, they mean maximize it overall. What else? This is absolute. It has nothing to do with the absolute value. Okay, so don't start taking absolute values of things. This has nothing to do with that. Which is why I'm going to try to say global a lot. Okay, so let's look for the global extreme of this thing. And yes, I understand this will be quite familiar to a lot of you. Okay, global maximum. The highest point of this thing is here. Okay, so there, f at A is our global maximum value. Okay, the value at the highest point. The lowest point is here. F at E. Global minimum value. Global minimum value. Good. Highest point, lowest point overall, or over the prescribed interval or set or domain. Okay? Okay. I said that the global maximum value, the global minimum value, so there's only one global minimum, only one global maximum at most, but you can hit that value more than once. So for example, let's look at sine x and I will label this very poorly indeed, or not at all. Okay, this thing's global minimum value is -1. Okay, and its global maximum value is 1 on its domain, the reals, and it hits its minimum and its maximum infinitely many times. Okay, it's possible to hit your your extreme values more than once. Okay. You can only have one global minimum and only one global maximum at most, but you can hit it multiple times. Okay. The title would be good here. Global Extrema. Okay, pay attention to the domain or the interval or the set or whatever that we're talking about. Okay, because that affects your answer. This is all the same sort of core function, okay, but we're changing the interval we're talking about. This is probably the simplest one. We'll start here. If you restrict the identity function, to the closed interval from 1 to 3, you'll see this thing has a minimum value and a maximum value, yeah? Minimum value there, maximum value there, life's good. Let's look at these other cases. Or let's look at, let's look at these other cases. Let's look at this one. If the interval is closed at 1 and open at 3, what happens? Yes, you've got a minimum value. You do not have a maximum value, okay? This thing has a tight bound on top, okay? There's a limit at the top, and it's 3. The trouble is this thing's open there, okay? It never reaches that point, okay? You never hit that value, so you'd love to say the maximum's 3, but it's not, because you never actually hit 3, okay? In other words, any point you give me, okay, that's on that curve, I can give you something higher, okay? Does that have any questions about that? Okay, again, this thing has no maximum. Similarly, this guy has no minimum, okay, because the range is open there. Open at both ends, no maximum, no minimum. And if you look at it on the entire real line, again, no maximum, no minimum, okay? So whatever point you find on here, I can find a higher one. Whatever point you find on here, I can find a lower one, okay? There's no highest point, there's no lowest point. So it has no maximum, it has no minimum, okay? And remember, infinity is not a number, it's not a valid x value, and it's not an attainable y value either, okay? Okay, look at that last example, look at that picture, and those are special cases of something that's true, the extreme value theorem. Okay, this is hard to prove, I'm not sure I've ever seen a proof of it. This is hard to prove. If f is continuous on a closed interval I, like that thing is, and like that last example over there was, then there exists a global maximum value of f on I and a global minimum value of f on I. Okay? Just picture it, it should make enough sense. Okay? You got a continuous function on a closed interval, then it's going to have a global max and a global min on that interval. Okay. When I say on the interval, somewhere in the interval. It could be in the interior, okay, as this guy was. It could be at the endpoints, as this guy was. The interval I'm talking about is an interval of x values. Okay, so in this case, when we're talking about these kinds of intervals, in this case we were talking about the interval from A to B closed at both ends. And closed means including the endpoints. What else? Extreme value theorem. The conditions matter. And again, I told you these are called hypotheses conditions in math. Okay? It better be a closed interval, and it better be continuous on that closed interval. Okay? Don't try to cheat that, because bad things will happen. Okay? The extreme value theorem has nothing to say when the interval is not closed or when you have a discontinuous function. So, for example, this guy, okay? We talked about this guy on R. R is an open interval, okay? It doesn't include those things that you want to treat as endpoints, which are infinities, okay? And yet this thing has maximum and minimum, okay? But in the last slide, when we talked about the line on R, or any of these other cases, bam, 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 you didn't have a maximum and a minimum value, okay? So the extreme value theorem does not guarantee the presence of minimum and maxima unless you've got a closed interval and you're continuous on it. Okay. For those interested in this kind of thing, I will just quickly show you two examples of where this goes wrong. So, for instance, here, Again, this is similar to what we just saw. Okay, this guy is continuous only on the open interval from A to B. Okay? But this guy has no minimum value, it has no maximum value. Okay? So again, the extreme value theorem has nothing to say about those kinds of cases. It doesn't say anything one way or the other. It could be that it has maximum minimum, it could be that it doesn't. Okay? In this case, it doesn't. Okay, so it's going to be open, it's got to be continuous. Okay, here we got a closed interval, but we have a discontinuity in the middle. 1 point of discontinuity. Even one discontinuity is enough to screw you up, okay? Even one discontinuity is enough to say extreme value theorem is impotent, we can't listen to it, it doesn't matter. It has nothing to say about these kinds of cases. Okay? This guy's one discontinuity in this closed interval, and look at it, it's got no minimum, it's got no maximum. Okay? So don't try applying that to anything that it shouldn't be applied to. As with L'Hopital, as with everything else. Okay? Questions about this? Yeah.
Do we consider a horizontal straight line?
Okay, what about it?
Like if it has a maximum or minimum on a closed period?
Yes, yeah, I was gonna do that, and I thought it was, yeah. So a horizontal straight line, by this definition, I think every single thing on it is a maximum, and every single point on it is a minimum, right? Yeah. It's open, so nothing's guaranteed, right? On the whole real line,
Yeah.
or on a closed interval.
On a closed interval.
Yeah, on a closed interval, then it's guaranteed to have a maximum and a minimum. And okay, so I'll do that. Thank you for saying that. That?
Yeah.
Yeah. Okay, so it's guaranteed a max and a min, and indeed it has it. It's just that the max and the min are both that, and it's achieving them everywhere. Okay, yeah? So the max doesn't have to beat everybody, it has to beat or tie everybody, and the min has to be less than or tie everybody. Does that make sense? Yeah. Yeah, so in this case, everything's a max and everything's a min. And the same is in fact true of the whole line. Yeah?
Would you say that everything's an absolute max and everything's an absolute
Yeah.
min? So then for like
And
the
local, for that guy.
sinusoidal function, if you have two periods,
Okay, withdrawn. I was talking about this thing. What are you talking about?
so if you have like a sinusoidal function
Yes.
with two periods,
Yes.
would you have two absolute maxes and two absolute mins?
Yeah, you have one absolute maximum value and one absolute minimum value, but you attain the maximum twice and you attain the minimum twice. Is that fair? Okay. Yeah.
If you had the horizontal line, but the points were exclusive, would
Yeah.
that still be the same?
If you have horizontal line and it's open, look guys, these are sort of sick counterexamples, and I wanted to skip this to not confuse folks. Thank you for asking. Like that?
Yes.
Looks a bit like Baymax's head. If you know what that is. Okay, yeah. Yeah, every point that is on there is still a max and a min, yeah. Again, you're not guaranteed anything, that guy doesn't want to talk about this, okay? But in this case, yeah, everything on there is associated with a max and with a min. But again, that's a special weird case. But thank you for asking. Okay. The lesson is don't apply that where it doesn't apply, that's all. Okay? Because weird stuff can happen. Okay. Excellent. Oh. Reconstruction. Okay, local extrema. Okay, the first step for us to identifying global maxima, global minima, are finding local maxima and local minima. So our first step to locating global extreme. By the way, if I give you an answer and it doesn't make any sense, don't do what I used to do, which is just nod and get rid of the guy who's giving you the answer, all right? So just tell me it made no sense. Okay. All right, so finding local extrema is our first step to finding global extrema. So what do I want to say? Okay, again, we got some painful definitions here. For local or relative extreme values, consider a function f, again, on an interval I in its domain, or a domain, or some set, or something like that. If there is a number c in I such that the value of the function at c beats or ties the value of the function everywhere else in I near c, this is the difference, the last time we didn't say near c, and that's why this is local, then f at c is a local or relative maximum value of f on I. Similarly for minimum. Okay, so what were we talking about before? We were talking about values that beat or tie the value of the function everywhere else. Now we're talking about the values of the function that beat or tie the values of the function nearby. Okay, hence local. Okay, so you don't have to beat everybody, just beat everybody in your neighborhood. Okay, notice I said a, not the local max and min. Okay, because you can have more than one local max and min value over some domain. Be warned, we're using a slightly different definition in this course than you might see in other places. So the Stewart textbook does this a bit differently, okay? So it's going to talk about local maxes and local mins differently than we are. If you're interested in that, let me know. We're going to use a perfectly sensible definition here. It's just that given what the word near means in math and what neighborhood means in math and what Stewart does, this isn't quite consistent with that. But do what I'm talking about and you'll be fine. Okay. Let's look for local extreme values on this guy. All right, so over here, we're beating everyone around us. Okay, beating or tying everybody nearby. Okay? So this is a local max. Okay, so this is a local maximum value as well as a global maximum value. Here we have a local min. Okay, because we're lower than or tying everybody nearby, and I mean immediately nearby. Okay, we've got another local max here. And like I said, you can have more than one local maximum value, you can have more than one local minimum value, hence this kind of thing. That's a local min. Okay, that's a local min because it's under or tying everyone in its immediate neighborhood. And notice that local min is also a global min. And finally, this guy beats or ties everybody in its immediate neighborhood. It's a local max. Okay, so beats or ties everyone in its immediate neighborhood is probably easier to remember than that first point there. Okay, remember this in a way that makes sense to you. Local max, local min, local max. Good? All right. Yes, sir.
So point A, f of A is a local max and an absolute max?
Yeah, that's right. Okay, that's right. Excellent. Okay. Every global extremum is also a local extremum. You'll notice that here, right? This global guy was also a local guy. This global guy was also a local guy. Every global extremum, thank you, is also a local extremum. Okay? To be the best in the country, you've got to be the best in your neighborhood. Okay? That's it. But if you're best in the neighborhood, that doesn't mean you're necessarily best in the country. So not every local extremum is going to be a global extremum. Okay? Simple as that. And we saw that there. Okay. So local extrema are essentially candidates global extrema. Okay, if you can list all the local extrema, the global extrema are a subset of that. Okay, good? Alright, so typically what we're doing is we're looking for global maxima, global minima. We want to see the best we can do overall, not just in the neighborhood. That would be silly. So what we do first is we look for the local extrema and we try to winnow that down to the global extrema. So the question is, how the heck do we find the local extrema? How do we find local extrema? Okay, let's look over here. Let's see where we found local extrema. We found them at the endpoints. Oh, okay, I'll say one thing. This thing, for instance, in the Stewart textbook, isn't going to happen. Okay? But in our world, does. Just a warning for anyone who's using that textbook or anything too advanced. Okay. Let's look at the local extrema. Where are we seeing them? We're seeing them at the endpoints. We're seeing them there. Okay, those are called stationary points. They're where the tangent is horizontal. And we can see them there. And what's going on there? You're not differentiable there. Good? Okay, so in this picture, which I've drawn to show these points, you can have local extrema at endpoints, at points of non-differentiability, and at stationary points where the tangent is horizontal. Okay. Hey, look, a name. Critical points. A critical number or critical point of a function f is a number c in its domain where either the derivative is 0 or the derivative does not exist. Okay? So, that guy are all critical numbers. Okay? So again, critical numbers include where you're not differentiable and where you're stationary, where the tangent is flat. Okay. I'll just put a title, critical points. Does that make sense? Okay, that's not the whole list of candidates for local extrema. There's more. Okay, here, I'll go back a slide because I saw too many hands down. All right. Okay, so again, critical points are where you have no derivative or the derivative is 0. Okay, and again, we said where can the local extrema occur? Either at those kinds of critical points, or at endpoints. And that's what this is going to say. This isn't quite Fermat's theorem, it's a corollary to Fermat's theorem, so it follows from it, essentially. Consider a function f on a closed interval I in its domain. Again, I'm being overly strict, it doesn't really have to be a closed interval I in its domain, it could be on its domain or a domain. If f has a local extremum, okay, either local min or local max on I at C, then either C is a critical number of f or C is an endpoint of the interval. Okay? So in this case, now we've included everything. Okay? The candidates for local extrema are only the endpoints and the critical points. And that's it. Okay? That's a full list of candidates. Okay? So the critical points and endpoints are the candidates for local extrema, and the local extrema are candidates for global extrema.
Can you write that down?
Yeah. Okay, where are we here? Fermat. Just make sure I've read what I want to say. Yeah. The proof for this is reasonably nice, if you're the kind of person who likes proofs. Okay, good. So what are we saying? The critical points and endpoints give us the full list of candidates for local extrema. Good? And that's all that's saying. Okay, we are not saying that every critical point corresponds to a local extrema. Over here. Do not think that every critical point or number gives a local extrema. Okay, it's a list of candidates. Some of them won't make it.
That'd be like x to the 3.
Very good. Very good. X to the 3. Okay, we've got a horizontal tangent there, but there's no local extremum there, okay, on R. Okay, the line just goes through it, okay? That's not a max or a min, and yet the tangent is horizontal there, okay? So over here, we have a critical point because the derivative at 0 is 0, but no local extremum. Okay, another example. Very creatively come up with is the cube root. Okay, we have a vertical tangent there, even though it doesn't look like that with my picture. There's a vertical tangent there. The derivative at 0 does not exist. Okay, so it's a critical point, but there's no local extremum there either. You're just running through it. It's a list of candidates, not everybody makes it. Okay, next class we're going to be talking about, and some of you probably already know the rules for this, we're going to be talking about which critical points will give local extreme. That's next class. I'm trying to keep that picture there, in case I need it. Okay, do not forget to check endpoints. Endpoints where the derivative does not exist, as well as stationary points. Okay, I've forgotten this in the past. Don't make a mistake, okay? Okay? You've got to check all those things, all the critical values, including non-differentiability and stationary, and you've got to check endpoints. Okay. Okay, for instance, if you forgot to check endpoints, you'd miss those two guys. If you forgot to check points of non-differentiability, you'd miss that guy. Okay? Okay. Now, what did I say? The thing that I raised? I said that if you're global, you've got to also be local, right? If you're the best in the country, you've also got to be the best in your neighborhood. So that also provides a list of global extrema, okay? Of candidates for global extrema, okay? Which is what that last line is trying to say, okay? So we said that the critical numbers and the endpoints provide a list of candidates for local extrema. Because all global extrema are also local extrema, this also provides a list of candidates for global extrema, okay? That's all that last line says. Okay. So critical points and endpoints give a list of candidates for local, and local is essentially gives a list of candidates for global. Okay, so now we have a list of candidates. Let's pick our Donald and our Hillary. Incidentally, if you do optimization and you manage to find Donald and Hillary, please try the problem again. Fermat's theorem. Okay, you look this up on Math World or Wikipedia and it goes, there ain't one, right? There are so many theorems due to Fermat that the term Fermat's theorem is best avoided unless augmented by a description of which theorem of Fermat is under discussion. He's an important guy. He did a lot of stuff, okay? You may have heard of Fermat's last theorem, which took 350 years to resolve, okay? And originated from just him writing a marginal note in his book, where he said, I have a truly wondrous proof of this, which this margin is too small to contain, and he didn't have one, and people spent 350 years trying to find it. What's that? They found it, and there's nothing he could have done. It's just crazy. Okay, and Fermat's principle there, okay, about the pathing by ray of light. That turns up in the story version of the film Arrival, if you ever read that. And it's a thing in optics, and it involves optimization, okay? So it's talking about how light takes the path of least time. So that's an optimization thing itself. So just a side note on Fermat being important. Okay. We're going to restrict our attention to finding global extrema of a continuous function on a closed interval, okay? So again, continuous, closed. And that keeps weird stuff from happening, and it keeps us from having to think too hard. Okay? So we just follow the steps and life's good. You don't have to be too creative or imaginative or brilliant to do this. Again, if you didn't write it, do write what I said at the end there. That the critical points and endpoints provide a candidate list both for local extrema and for global extrema. Okay. Let's see how much of this I can do. Okay, what are we going to do? We're going to find the critical numbers, and then we're going to evaluate the function at the endpoints and at the critical numbers. Okay? The biggest value we find is the maximum. The smallest value we find is the minimum. Easy peasy. All right, let's see how much I can do. Here's our example. Find the global maximum and minimum values find the global maximum and minimum values of f at x equals 5 minus 2 cos x plus x over the interval 0 to pi. Is the interval closed? Does it include its endpoints? Yeah. Closed. Okay. Is this function continuous on that interval? Yeah, it's continuous everywhere, okay? That's continuous. Trig functions are continuous. That's really continuous. Add them up, you get something continuous. So yes, we got something continuous. So we can use that. All right. Step 1, find critical points. Find critical points or critical numbers. To do that, you've got to find the derivative, okay? Because it's where the derivative doesn't exist or is 0. Derivative of 5 is 0. Derivative of this guy is minus 2 times minus sine x, so 2 sine x. Derivative of x is 1. Okay. Where is the derivative undefined? Do not forget this. Where is the derivative undefined? Nowhere. This is a nice function. It's differentiable everywhere. Nowhere. Where is the derivative 0? Let's see. 0 equals 2 sine x plus 1. It's the same as sine x. Bring the 1 over. Minus 1 divided by 2 minus 1/2. Okay? So we're looking for solutions of that on that interval. That's an R. On the interval from 0 to 2 pi, the solutions are 7 pi over 6 and 11 pi over 6. Which might be midterm familiar numbers, maybe. Okay, convince yourself of that, draw a picture, do whatever you do, draw a circle, or a graph. Okay, don't forget to stay in bounds. Okay, we don't care about critical points that aren't in the interval, only write the critical ones that are. Make sure you're looking for zeros of the derivative, not of the function itself. That would be silly. And if it's hard to find the zeros of the derivative, what do we do really, really hard? We use a root finding algorithm. Okay, one of the big reasons we have root finding algorithms are to optimize, to find the zeros of the derivative. Okay, I'm going to wrap this up next time so you can go. We'll start from there. Thanks, everybody. Okay, we were talking about extreme values last time. And we talked about the closed interval method. And we started an example. And between then and now, I added this as an overview. So if you want to write that down or look on the list. Okay, a semi-big picture idea of what the heck we were talking about. Okay, so suppose we want to find the global maximum and minimum of something, of a function on some domain. The critical points and endpoints, okay, the critical points being where the derivative doesn't exist or is 0. The critical points and the endpoints form a list of candidates for local extrema, and because all global extrema must be local extrema, also a list of candidates for global extrema. A function that's continuous on a closed interval is guaranteed to have a maximum and a minimum on that interval. And finding such maximum and minimum is easy. Okay? All you do is you list the critical points and the endpoints, you evaluate the function there, and then you pick the biggest and smallest values. And that's it. Okay? So again, list the critical points and endpoints, evaluate the function there, pick the biggest number, call it a maximum, pick the smallest number, call it a minimum, and you're finished. Okay? Notice that at no point did we actually have to find out which critical points correspond to local extrema or anything like that. Okay, if we're looking for global extrema, we just list candidates and evaluate. We don't have to think about what's a local extrema and what isn't. Okay? Okay, so at some point I told you that local extrema are candidates for global extrema, and that our first step in finding the globals is to find the locals. We don't actually have to do that. We don't actually have to find the locals. We just find the candidates for the locals, which then acts as a list of candidates for the globals, and from that list of candidates we find the globals. Okay? Read that, think about what I said. If it doesn't make sense, ask me, including now. Okay? Okay. Again, when we're finding global extrema, we don't specifically actually have to find the local extrema. Okay. So we'll finish that example now. No questions? Even after that, huh? Okay. Again, that should all make sense, and I put that there to clarify things. Okay. So our example was, we were going to find the global max and min of this thing. Again, if you were writing last time, you'd have most of this. Okay, we're looking for the global extrema of that function over the interval or the domain 0 to pi. Okay, and we want to use the closed interval method, hopefully. So we check, is the interval closed? Yes. Is our function continuous on that interval? Yes. Okay, this thing is continuous everywhere, so it's continuous on that interval. And again, closed means you include both your endpoints. You've got square brackets. Okay. Now our job is to find the critical points. So find critical points. critical points of the function, which is where the derivative fails to exist or is 0. Okay, what's the derivative of this thing? 0 minus 2 minus sine x, so plus 2 sine x plus 1. Okay? Alright, the critical points. We need to find where this thing does not exist. Where is this guy undefined? Don't forget to check that. And the answer in this case is nowhere. We're good? Okay, where's the derivative undefined? And it's nowhere. This thing's differentiable everywhere. And now, where is the derivative 0? Okay, so we have to find where this thing is 0. Bring the 1 over, divide by 2. Okay, and now we have to solve this thing on that interval, and only on that interval, or on the inside if you want. Open or closed, whatever. The solutions are seven pi over 6 and 11 pi over 6. Okay, find that however you like to find these things. For instance, on the circle, it would be here. Seven pi over 6 and 11 pi over 6. Okay, and each of those gives sine minus 1/2. All good? Okay, again, you don't care what the solutions are outside of that interval. Okay. Okay, so what are our critical points? There's nothing here. There's those two guys there. So our critical points are those two. Okay, and life's easy now. Just evaluate the function there. Evaluate the function, let's say f, at the critical points and endpoints. Okay. You can get some of these exactly, but then they become hard to compare. So I'll just write out what I'm evaluating, what the value is, and if you can't get that, let me know. Okay, endpoint 0. We get exactly 3. What else we got? Critical point. The first critical point, 7 pi over 6. We get approximately, okay, just plug that into f, and we get what? Approximately 10.397. The other critical point, we get approximately 9.028. And the second endpoint, 2 pi, we get approximately 9.283. Okay? All right, very good. Okay, check the conditions, find the derivative, find the critical points. Evaluate the function of the critical points and endpoints. And you've got this list, and now just pick the big one and the small one, and that's it. Okay? So what do we got? Smallest one is here. Okay, that's your global minimum value. Or global minimum. And what's the biggest one? This guy. Global max value on that interval. global minimum value is this, achieved at 0. The global maximum value is this, achieved at 7, 5, or 6. All right. Good. Okay, so reminders. 1, do not forget to check where the derivative is undefined. In this case, it was nowhere. It won't always be that, okay? So don't forget to check this. This is part of the critical points. When you're trying to see where the derivative is 0, you want to see where the derivative is 0, okay? Not where the function is 0. So don't set this equal to 0 and solve that, okay? That's pointless. If it's hard to find zeros, what we do is we use the root finding algorithm, okay? Probably not on a test, but in practice, if we need to find zeros of the derivative, okay? And if this was a lot uglier than this and hard to solve, then what would we do? We'd use a root finding algorithm, and that's one of the big reasons we have root finding algorithms for optimization. What else? Finally, when you're evaluating, don't forget the endpoints, okay? So you evaluated the endpoints and at all the critical points, and then you pick the big and the small, and you finish. Okay? So it's just a bunch of don't forgets. And that's it for that example. Any questions about that before we go on? Okay, there's your picture. Okay, I made the line solid inside the domain we're talking about. There is our global minimum at 0, having value 3. And there's our global maximum. There's our other critical point, which we don't care about because it's not a global anything. And there's our other endpoint, which we don't care about because it's not a global anything. Okay?